Hello! In this session, we are going to have a look at Altair FluxMotor. In particular, I am going to show you how to perform electromagnetic analysis of a motor using it. To start, let's have a look at the agenda of this short video. First, I'm going to do a brief introduction about Altair FluxMotor. Then I'll do a demo on how to design, perform electromagnetic studies and export results with this tool. We will end with some keynotes about FluxMotor. If you are interested in thermal or MVH analysis, don't miss the upcoming videos. What is Altair FluxMotor? So it's a dedicated standalone and multi-physics environment to accelerate the design of e-motor concepts. It allows an efficient machine pre-design and quick performance evaluation. Thanks to the intuitive interface and workflow, it is accessible to a broad range of users. The embedded finite element technique makes it fast and accurate. We have an effective machine parts management, and the customization is also possible. A lot of parameterized parts are available in the part libraries, depends on the topology. FluxMotor can also help us to have an efficient project management thanks to the possibility to create new user motor catalog. It also contains a comparator where we can add different motors and see the overall dimension, the weight, performance index like the power density and the machine constants. And last, it gave us the possibility to continue to work on our project with advanced Altair tools in an easy way. Altair FluxMotor is mainly for radial flux machine design, but is constantly evolving. In fact, the developers team is working on axial flux machine that will be available soon. Today, you can find synchronous machine with permanent magnets, inner and outer rotor, reluctance synchronous machine, induction machine with squirrel cage, inner and outer rotor, and also the possibility to add skewing to slots, magnets, and bars. Let's start with the demo, and let me go to the FluxMotor supervisor. You can see the supervisor of Altair FluxMotor, and we want to start with the motor catalog to show you how to create a new catalog for your project. So we have to click on catalog, add. In my case, the project is short video. We can keep the family, the type and the subtype, and we can see the new catalog here, but we want to start from an existing model. So we can take the Prius 2010 and click on edit. We have the possibility to modify the name and choose the catalog that we want to use. So we can see that in the short video catalog we have the new motor and the motor factory will appear. The motor factory is the most important tool of FluxMotor, and here we have the possibility to change all the design of the motor. In the test section, we can find the predefined test, and also in the export section, we have the possibility to export the results and the model, the FluxMotor model. Housing, shaft, and the cooling section are mainly dedicated to the thermal analysis, so let me start with the topology. Here we have the possibility to enter the overall dimension and the configuration. In fact, we can find the outer diameter for the stator, the number of slots, and the number of poles. Going to the rotor section, we can find the possibility to change the magnet shape. We can click on it and we can find all the rotor parts that are available in the part library that is accessible from the Flux supervisor. We don't want to change the rotor shape, but you can see that clicking on one of them, you can see all the parameters available for this part. So for our part, that is here, we can find some inputs parameter that you can modify. Clicking on it, you can enter a new values, but also you can see in the graphical view the meaning. Output parameters are just computed starting from the main one here. We have the possibility to enter and to consider the skew for the rotor and for the stator, both of them. And we can go to the polarization option, where we can check the polarization of the magnets. In the stator section, we have again the possibility to change the slot shape and to add the skew, to consider a different lamination type, like, yes, we can want to continue with that store the model, like the rectangular one, the square shape. And in the design, we will find the inputs of this slot part, all the parameters that we can change. For example, we suppose that we want to change this to 5. And we can also use the undo action. In the winding section, we can define the winding connection and the definition mode of the winding scheme. By default, you can see that we are using the auto, but we can complex the definition mode, adding some parameters, for example, the number of layers, the number of parallel paths, to arrive to the expert mode that allow us to enter each coil manually. So also the coil section is quite important to compute oscillosis, so we can choose the wire topology that can be circular or rectangular, the slot filling, and the conductor grouping method. We also have an insulation tab that are mainly used for the thermal analysis, and we can define the end winding geometry. Also the air pin can be used. So once you define your winding scheme, we can check, for example, the layout that are available also for the export, the radial layout, the MMF, spatial and harmonics, and the table, the winding factor, and at the end the slot start to check if the winding scheme is balanced or not. The last section is the materials one, and we can define all the materials of our motor, starting from the magnets. You can find a predefined material for the magnet, that is the neodymium, but you can choose between different materials that are available in our library, and you can add also your own material, both for magnets and for the magnetic circuit. So let's start with the predefined electromagnetic test inside available in FluxMotor, just because this short video is dedicated just to the electromagnetic tests that we have. So we can start with the open circuit tests that are the cog in torque and the back MF. So by default, the cog in torque doesn't require any parameter. We have the possibility to enter the temperature for the magnets here, and we have some optional parameter that is, for example, the number of computation per cogging period that influences the accuracy of results and the computation time. The default value is equal to 45 and the minimum allowed is 13. So just to speed up the computation, let me set it to 20. We have to click on apply inputs, the other parameter, and we can start the test. The other parameter are the maximum harmonic order, the rotor initial position, and the air gap mesh coefficients. That is a coefficients that allow us to set a bit the coefficients in the air gap of the finite element model that is embedded. So in a few minutes, the results will appear in the left of the screen. Here we have the results. We will have the results, and we can visualize the results in the main window. The main results of this test are the cog in torque curve and the detail of this torque. So we obtain the results. We can click on these buttons here to check the inputs, the settings, and the magnet characteristics that we set in the design part. Then we can obtain the results, so the mag flux, the magnetic flux density in each part of the motor, and the period of the cog in torque, and the magnitude peak to peak of the cogging torque. So we can move the cursor along the curve to check some points. We also have the harmonic analysis, the results of the harmonic analysis on a graph and in the table here. So we can continue with the back MF. In this case, the back MF requires just the input as input parameter, the speed, and we have also the thermal as option for the magnets. But we have also other parameters like the number of computation per electrical period that influences the accuracy of results and the computation time. The default value is equal to 50, then the minimum allowed is 13. So let me put it as 15. The maximum harmonic order, the rotor initial position. The computation are performed by considering a relative angular position between the rotor and the stator, and the relative angular position corresponds to the angular distance between direct axis of the rotor north pole and the axis of the stator phase 1, that is the reference phase. So according to the input, the rotor initial position mode, the angular position can be defined either automatically using an internal process of FluxMotor. So we can leave auto, click on apply inputs and start the computation. As outputs, we will have the back MF, the voltage constant, the flux linkage, and the flux in the air gap, the flux density in the iron, and the magnet behavior. And here we can see all the results available. So we already obtained the results, and we can check the inputs settings. The inputs is just the speed in this case, the winding and magnets characteristics, and we can obtain here the main results in the open circuit table. So we have the KE, the constant, the phase voltage, first harmonic, the line voltage, and the flux linkage, the flux in the air gap, flux density in iron, and the magnet behavior. Here we can see the curves of the voltages versus time in open circuit. That is the results that we are waiting for, and the harmonic analysis on it. So we also have the correspondent table and the line voltage versus time in open circuit with the harmonic analysis in the graph and in the table. Also, we can check the flux density in the air gap versus angular position with the harmonic analysis and the flux linkage versus rotor angular position. The last output is the graph in the graphic view and is the flux density, the ISO values of the flux density on the motor. We have a periodic motor here, as you can see, to speed up the computation. So we are considering periodicity for this motor. We can check the mesh and plot the vector potential, so the ISO lines. If we are interested in another speed, we can just change the speed, click on apply and start. And we can see the number 2 here in the back MF. So we can continue with the model. The aim of the test characterization model motor maps is to give 2D maps in JD/JQ plane for characterizing the three-phase synchronous machine with permanent magnets. These maps allow predicting the behavior of the electrical rotating machine at a system level to provide accurate maps ready to be used in system simulation software like Activate. So we have the possibility to enter the thermal of the magnets and of the winding. We can consider the electronics, so we can consider the maximum efficiency and the rated power, and certain mechanics law that allow us to consider the losses, mechanic losses. As inputs, we have to put the operating quadrants, that it defines the quadrants in the JD/JQ plane where the test will be carried out, the maximum current density or the maximum line current, and the maximum speed. We can also enter some additional parameter like the number of computation for JD/JQ, the number of computation for speed, that decide how many computation points in this test FluxMotor has to be done. And yeah, it Also, the time can be changed a bit. So in my case, I'm using the lower values that I can use just to speed up the computation. So we can click on Start and waiting for the results. The results will be the coupling fluxes, the dynamic inductances, the dynamic cross inductance, Mach flux, the Mach torque, and all the losses. So we can check the input, and all the maps are available here and can be exported. So the phi, all the fluxes, the inductances, dynamic cross and static, the Mach torque, and the iron losses, Joule losses, and total losses. The power electronic and the mechanical losses are not available since I didn't enter any values. So also we can track the flux due to the magnet here. And yeah, we can go to the next test, that is the datasheet test, where we have to enter current and voltage. The aim of this test, characterization datasheet motor, is to characterize the behavior of the machine when operating at the working point that is located at the base speed point. So the working point or base speed point of the torque speed curve is defined by considering the maximum allowed line voltage and the maximum allowed line current. For this working point, general data of the machine like machine constants, power balance, and magnet behavior are computed and displayed. So the magnetic flux density is also computed in every part of the machine to evaluate the design. The test results also include all the necessary constants to build the equivalent model of the machine and to simulate the behavior of the machine in its electrical environment. An overview of the machine performance at no load is also given in this test. So for the parameter, we have thermal, electronics, and mechanics as before, and we have the max line current, or we can use the max current density, the max line voltage, and the command mode. For the additional, that can be changed between maximum torque per voltage or maximum torque per ampere per current. So the other parameter are the additional losses here that is used to consider losses which are not computed, like losses due to the eddy current, proximity effect, due to electronic devices. These additional losses will be considered for computation of power balance and efficiency. The default value is 0. It means that the power balance is computed without considering additional losses. We have done the number of computation for control angle, the number of computation for electric period, the number of computation for ripple period, and the current coefficients. That is, the linear condition must be considered to compute unsaturated inductances, and to obtain a linear magnetic behavior for materials used in the magnetic circuit, the current coefficient is used to define the corresponding maximum current, which still allows linear condition, so to consider the magnetic behavior. From practical point of view, the maximum phase current is multiplied by this current coefficient. Thus, the resulting current is used to compute the unsaturated inductances. So we can leave 0.05, and yeah, other parameter we already know. We can just click on apply and start the test. Since this test takes some time, I decided to solve the model. So we can check the results, and in particular we can go to the main result, base speed, and check the mechanical torque, the base speed, and the relative speed. So we have the mechanical power, the machine efficiency, and the control angle. Then the line current RMS, the line voltage, so all the data like the machine electrical power and so on, so all the data of the machine at the base point. We also have the machine constants available, the KT and the KE. Other results that we already seen in the previous computation. Also the ripple mechanical torque are computed, and we have the ripple peak to peak, the ripple values peak to peak, and we can track it on the graphs. Quite important is the mechanical torque versus current and control angle that we can track, and phase voltage versus time in open circuit, all the data in open circuit that we already seen in the previous test. So also the flux density in the air gap versus rotor angular position. The accuracy, as you can see, it depends on the number of points that we set here. We can continue with the next test, that is the working point with sim wave drive. We have three possibilities to enter: current, control angle and speed, torque and speed, and current and voltage. So two computation methods are available. The fast computation mode is perfectly suited with the pre-design step. It's an hybrid model based on magnetostatic finite element computation and Park transformation theory. So we will use this one to speed up the computation in our case, but also the accurate method is available that is perfectly suited with the final design step. So pure finite element modeling based on transient computation will be carried out for in this case. So the AC losses with accurate computation mode is available, and we have three different types of analysis. So finite element hybrid, that is the most faster in this case, is the faster one. The finite element one phase to arrive to the finite element all phases that require more time than the other. So, but in this case, we can choose fast. We can set the current density, the control angle, and the speed for sure. And we can also choose if we want to take into account the ripple torque or not. This also requires more time. So we can click on apply inputs and click on play. And in a few seconds, we will have the behavior of the machine at this specific working point. In fact, we can go to the working point table here. We can see in blue the parameters that we entered, and in black the parameters that we obtained from the simulation. So we can see the mechanical torque, the machine efficiency, the mechanical power, also the machine constants and the power balance are carried out. And we have the flux density in iron, but we can check it also in the last graphic that allow us to see the ISO values on the machine. And we have also the flux density versus mechanical angle. Well, the last test is the performance mapping. So here, the aim of the test is to characterize the behavior of the machine in the torque speed area. Input parameters are the max line current or the current density, as before, the max line voltage. We have two types of command mode, are the maximum torque per volt command mode and the maximum torque per amps command mode. Whatever is the applied command mode, the first step of the process consists of computing the torque speed curve, and the second step is to compute the efficiency map bounded by the torque speed curve. So in function of the command mode, the applied process of computation is different to obtain curves and maps. So additional losses input is not available. The maximum speed normally can be minor or major respect to the base working point. We can enter a user working point, so a single one or a duty cycle also. And we have other, option that are, for example, in this case refers to the duty cycle. We can enter the values in the table, in the FluxMotor table, or just enter an Excel file. So we have the number of computation here that we can perform. We can change the parameters and just click on apply and start the test. In our case, we already have the results here just for time reasons. So in the results, the performance of the machine at the base speed point and for the maximum speed here. So a set of curves like torque speed curve and current versus speed, voltage versus speed, control angle versus speed, power versus speed. So a lot of curves that allow us to well understand the behavior of the machine and the maps. In addition, we have in JD and JQ plane, a graph shows the computed working point for the torque speed curve. The ISO electromagnetic torque and ISO current and ISO voltage are also displayed in JD and JQ plane. So the results help the user to understand the possible performance of the machine in its electric environment. So the accuracy will depend for sure on the values that we put here. So yeah, these are mainly the results. We can also consider the temperature with the duty cycle, but we have to use the duty cycle as option here. Then the 2D maps are available at this section. We have the efficiency of the machine, the current, the voltage, the control angle in torque speed area, the power factor, and the losses. So we can go to the last section, that is the export, just to see that we have the possibility to export a report in an easy way. We can choose the design parameter and the test that we performed, so the material, and we can just click on apply inputs and see the PDF file that will be created. We also have the possibility to export the model directly for Flux 2D SKU, but also 3D, and the model for the optimizator, that is our hyperstudy. Also, the lookup table can be exported here. So just to summarize, let me come back to the presentation. We see a FluxMotor that is an efficient multi-physics machine per design and quick performance evaluation. Some keynotes are powered by finite element analysis that give us, I guess, ratio between quick computation and accuracy of results. Quick and easy design thanks to the part libraries that offers a lot of parameterized parts. Straightforward workflow, automatic visualization and export. So we also have the automatic link with the same license to the finite element domain, Flux for advanced analysis, to the optimizer that is hyperstudy, and to the system simulation through Activate and PSIM. And it is also an efficient project management with built-in comparator. So thanks for watching the video, and bye.